A common fractal shape in our beginning our study of fractals is the Sierpinski Triangle. This is a rough version of it that I've drawn. To begin the Sierpinski Triangle, we start with a triangle. Then we remove the center portion of the triangle. We continue this, removing the center portion, over and over. Here I'm going to remove the center portion of these three triangles to where we have nine smaller triangles now left. The darkened spaces, this is where there are no longer a triangle. In order to calculate the Hausdorff fractal dimension of this, we calculate D equals log n over log m. If we go from a factor with our initial triangle and remove the center piece, as we have here, then this would be our first triangle, this right here. This would be our second triangle, and this would be our third triangle. We could write log 3, because there's three similar triangles now, when the magnification factor is 2. This is an exact value for the Hausdorff dimension. Now if we go to a magnification factor of 4, then we can count the number of triangles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 triangles. We can write log 9. If you remember your properties of logarithms, then we can write log 9 over log 4 as 2 log 3 over 2 log 2. Of course, 2 over 2 cancels itself out, and we are left with log 3 over log 4. If we continue this process of removing the center triangle ad infinitum, we get something that looks a little bit like this. I have drawn this out for 6 generations, and theoretically I would continue further and further, removing the center triangle here, and then the center triangle, the ones I've left, right there, and it gets harder and harder to do that. But the key point is that the fractal dimension, the degree of self-similarity, remains the same. In our case, we have the number log 3 over log 2. We can find the decimal version of that, but this, however, is exact. The exact value.